Section 3.3. And Miss Mallory, I have that for you.
Yes.
Thank you, thank you. All right. If I had given you this first example in last night's homework, say like nothing about that exists, and I just said find the derivative of that function, tell me how you would have done it.
Find it out.
Because that's all you know how to do so far is take derivatives term by term. So let's go ahead and do the problem like we would have done it last night, right here. Multiplying before differentiating. If we multiply those two binomials, we would get 6x to the fourth, and then minus 12x, and plus 5x cubed, and minus 10. And then double check it. 6x to the fourth minus 12x plus 5x cubed, down the typo, minus 10. And then you could take the derivative. What would you get for the derivative? Okay, doesn't matter which order you have those in. If you want to put it in descending order, you'd have 15x cubed and then 15x squared, and then what? Minus 12. Anything else? That's it, because the derivative of a constant 0. So that's what we would have gotten. And if that were as difficult a product as we ever had, we wouldn't talk about the product rule. I'd just say if you got a binomial times a binomial, fold it out, take the derivative term by term. That's not a problem. But what about number 6? Could you have done this one last night? No, there's no way that you can write that so that it's not a product. It's square root of x. You could have written that as x to the 1/2, but you still would have had a product. And you don't have a rule that says you can take the derivative of a product factor by factor. There are a lot of things that you can do with factors that you can't do with terms, and some things that you can do with terms that you can't do with factors. So we don't have a product rule yet, but that's what's at the top of the page. Today's the product rule and the quotient rule. Product rule first. The derivative of f times g isn't just the derivative of f times the derivative of g. It's the first times the derivative of the second plus the second times the derivative of the first. And we could do some by the definition to prove that it works and to prove that it's true. Or we can just try the product rule on this problem and see if we get the same answer. And if we get the same answer, kind of trust the person that wrote the book and invented calculus, but the product rule actually works. I want to go back to the definition. All right, so let's try this by the product rule. And what I just said, I said these words instead of that formula. These words are what I say to myself when I'm taking the derivative of a product. First derivative of the second plus second derivative of the first. By the way, would it matter if I switch these two terms, if I took the second derivative of the first plus the first derivative of the second? No, they're added. Added doesn't matter. Addition, order, doesn't matter when you're multiplying. So it wouldn't matter in what order I did those two things. All right, so let's just stick with the first. Here's the first times the derivative of the second. What's the derivative of x cubed minus 2? 3x squared. Is it okay if I just write that out front because that's where I usually like my monomials? Yeah, that's the first times the derivative of the second. Now I'm ready for the second times the derivative of the first. What's the derivative of the first? 6. Let's see if that simplifies to the same thing that we got right here. Distribute. And then I have like terms that I can combine. But when I combine those terms, sure enough, I get the very same thing that I got by distributing first. So that really is only proof that the product rule works on that problem. Proving that it works on one problem doesn't prove that it works on all problems. But again, the only way to prove that it works on all problems is to go back to the original definition, and that is done in the book. You can look at it if you just want to see why that always works, but if you trust it, let's use it on example 6. I would take the step of writing that square root of x as x to the 1/2. And that's just rewriting the function. I haven't done any calculus yet. I just rewrote the function in a different way. But now I'm ready to take the derivative. All right, here's the first. X to the 1/2. What's the derivative of the second factor? Cosine x. That's the first times the derivative of the second. I'm ready for plus the second. And notice how I'm leaving myself a little bit of room here. It's because I know I like my monomial factor out front. That's the second times, what's the derivative of the first here? Definitely 1/2 x to the something, and what does the something need to be? Negative 1/2. Oh my. You remember those simplifying expressions from calculus? This is where they came from. They came from the product rule. I knew there would come a day when you needed to be able to factor out a fractional coefficient and an x, maybe with a negative exponent, maybe with a fractional exponent. This is what we were practicing for right there. So it is a goal of ours. When we write a derivative and we say, how do I know when to stop? Can I stop right here? The answer is no, don't stop right there. What we're going for 90% of the time, maybe 99% of the time, is the derivative written as a single fraction, if fractions are involved, with no negative exponents, factored completely as possible. Those 3 things are our goal. Single fraction, if fractions are involved, no negative exponents, and everything factored as completely as possible, so that if we had this set it equal to 0, we could easily. All right, with that goal in mind, what can we do to clean that up? Oh, I have a question. Can I multiply by 2 to clear out the fractions? Please say no, please say no. No, because this is not an equation. If it equals something, then I can multiply both sides by 2 to clear out the fractions. But that's not an equation. I can't just hocus pocus get rid of a fraction there. So with that out of the way, what's your next thought? Is there a GCF? You should factor out the fractional coefficient. If you're going to try to get this to be a single fraction, then you need to factor out the fractional coefficient and also x to the, how do you decide what power of x you could factor out? You can only factor out the lowest exponent. You can always factor out the lowest exponent of each factor. So 1/2 x to the negative 1/2 is my GCF. That's what I'm going to factor out, and then I'll end up bringing that to the denominator after this step. But I've got to have in parentheses or brackets what's left of each term if I factor that out. Whatever I put in brackets right here has to multiply times the GCF to give me back what I started with. So what would I have to multiply times 1/2 x to the negative 1/2 to get back this first term? I didn't hear you. Definitely starts with a 2 because I'd have to have 1/2 times 2 to get me back that coefficient of 1. I definitely have to have some power of x. And remember when I was trying to figure out what power of x I'm left with? These two have to add back together to give me positive 1/2. So the way to find this exponent I'm looking for is to subtract the exponent I factored out from the exponent that I started with. 1/2 minus negative 1/2 is 1/2 plus 1/2 is 1. And sure enough, if I add those together, I get back what I started with. I don't have to write that 1, but sometimes it just helps me so I can look at it and go, yeah, negative 1/2 plus 1 is positive 1/2. What else is left of that first term? Cosine x. All right, so that's what's left of the first term. Don't forget your plus. If you factor a GCF out of a binomial, what's left inside brackets has to be a binomial. If you don't put that plus down, you're going to end up multiplying everything left inside brackets. So what's left of my second term if I factor out this GCF? Just 1 sine x. And so how could that be written as a single fraction? Since I factored out an x with a negative exponent, what could I do with it? Bring it to the denominator. And a 1/2 out front, multiplying by 1/2 is the same as dividing by 2. So I can put that 2 in the denominator with x to the positive 1/2, or means either one's okay. My best guess is that in the back of the book, they'll change that back to 2 square root of x with this guideline in mind. If the original problem has radicals in them, the book will usually change the exponent back to a radical. But it would be absolutely okay with me if you left that 2x to the 1/2, that's fine. I'm just telling you what the book usually does, change it back to square root, but only because the original problem was written in terms of square root. All right, so here's what we've been leading up to since before classes even began. About the second day of pre-calculus, we start simplifying things like this. We learn to factor out fractional coefficients, factor out ugly x to the negative fraction coefficients. If you can factor polynomials, you can factor these guys. The thing to keep in mind is it's checkable. If you're not sure, write something down in pencil and then make sure that it multiplies back together to give you what you started with. All right, any questions? Let's do some from the book because we need some more practice at this. If you haven't figured this out yet, I'm a labeler. I like everything labeled and in order in my notebook so that I have the page of type notes, and then right behind it I'll have this. I know they go together. Just because you know the product rule now doesn't mean you have to use it every time you see a product. You get to choose, and that's what makes grading calculus tests difficult. I'm trying to get a little pity from you now, because if some of you use the product rule and then some of you decide to distribute and then differentiate term by term, you can get different looking answers. And different looking answers is okay, but that means when I'm grading the test, I have to grade the problem the way you did it and see if you made a mistake, or see if your answer is equivalent to the answer that I have on my answer key. Which do you think would be easier here? Product rule or just distribute s to the 1/2? I'd probably agree with you. On that one, I wouldn't use the product rule. I would say that's s to the 1/2 times s squared plus 8. And when I distribute that s to the 1/2, it's s to the 5/2 plus 8s to the 1/2. Have I done any calculus yet? Nope, that's just rewriting the problem. That has to be clear on your paper. If you're not clear about labeling things, you might quit right there and think you're through. I've seen that before. I've seen folks stop right there, circle it, that's my answer. No, you haven't found a derivative yet. The derivative of s to the 5/2 plus 8s to the 1/2 would be what? You're going to get good at 5/2 minus 1 in your head? 5/2 minus 2/2 is 3/2 plus 4s to the negative 1/2. So that differentiation was pretty easy if I distributed the s to the 1/2 first. There's a trade-off though. If we're still going for, I want my answer, single fraction, no negative exponents, factored as completely as possible, I'm not going to leave that as my answer. I'm not even going to just put the s in the denominator. I want this a single fraction, which means I need to factor out the GCF and factor out the fractional coefficients. So what could I factor out of that expression? What coefficient? You can't factor a 2 out of a 5/2. I could, but it wouldn't be pretty. What could I factor out that would leave both coefficients being integers? Yeah, I could factor out a 1/2. I can factor out the denominator, 1 over the denominator, whatever the denominator is. And what power of s could I factor out? Lowest exponent is negative 1/2. That's the GCF. Now, if I factor that out of the first term, what's going to be left? Definitely a 5, because 1/2 times 5 gives me 5/2, and definitely some power of s. How do I find that power of s? 3/2 minus negative 1/2. 3/2 plus 1/2. 4/2, better known as 2. Be careful. If I factor out a 1/2 from a 4, what coefficient is here? Yeah, it's just got to be whatever you multiply times a 1/2 to get 4. And I factored out the s to the negative 1/2, so that second term inside brackets is not going to have an s. How could I write that as a single fraction, no negative exponents, factored completely as possible?
Squared plus d divided by 2 square root s.
Beautiful. And I really don't care if you write 2 square root of s or 2s to the 1/2. Either one's perfectly fine. My best guess is the back of the book will have square root of s because the original problem had square root of s. If you just check yourself every step of the way, you can do this. If you don't check yourself every step of the way, you're going to end up making what you call silly mistakes, and I call your bridge is still going to fall in. You've got to become OCD about checking here. Not OCD in every phase of your life, but OCD about checking that every line's equivalent to the line above it. All right, so that's a good one. Sounds like a t-shirt. I'm always looking for good math t-shirts. I've got one with a quadratic formula on it. And I've got one, I'll wear it for Halloween, never mind. The trade-off is if we had used the product rule here instead of distributing, the cleanup would have probably been easier. If you distribute then the cleanup's a little bit harder. It ends up being about the same amount of work either way. It's just, do you want your work on the front end or do you want your work on the back end? And that's something you'll decide as you practice. All right, number 14. Now, I like that one even better because you need it before you get to calculus. You need it in algebra as well. All right. Does anybody have their book open? I think that's an x square, isn't it? In the book, is that an x square or an x cubed?
Yes, X squared.
Okay, x squared minus 3x plus 2 times x cubed plus 1?
Yeah.
Okay, the directions say find f prime of x and f prime of c. So it's like an A part, B part. And just like on the previous problem, we can decide, I could actually multiply that out and then take the derivative term by term. My gut tells me that the cleanup would be sufficiently ugly on that to make it worth just going ahead and using the product rule to begin with. If somebody wants to multiply first and then differentiate, go ahead and do it, and we'll see at the end who has less work. The answer should end up being the same. All right, so if we're going to use the product rule, how does it begin? The first times what? Derivative of the second, which would be derivative of x cubed plus 1. 3x squared. I just like to write it out front because that's where I like my monomials. That's the first times the derivative of the second. Now we're ready for what? The second. Then what? Derivative of the first is what? 2x minus 3. So here's the first times the derivative of the second plus the second times the derivative of the first. If there was anything I could factor out, let me see. That would be x, this right here would be x minus 2, x minus 1. But I don't have a common factor with that term anyway. If I don't have anything to factor out, then I might as well just go ahead and clear out parentheses and combine like terms. Is that what you got? Will it factor? Actually, the theorem that we covered in pre-calculus yesterday was any polynomial function can be factored into linear and quadratic factors, but to do so may take the rational zeros theorem, and we don't even want to go there right now. So we're just gonna, that's good enough. If I had to set it equal to 0, then, and that will happen at some point, but it's not going to happen right now. At some point, if I had to set that equal to 0 and solve it, it would take the rational zeros theorem. Which if you don't remember right now, that's okay. We'll hit it. That's fabulous. It limits the infinitely many things that could possibly make that equal 0 to a small list that could make it 0. And it's not the most fun thing in the world, but anytime anytime you limit infinitely many possibilities down to a few possibilities, that's a good thing when you're solving equations. All right, so that one's done. Oh, well, actually, it's not done because it said find the derivative, and then it said find f prime of c. I don't even want to spend class time plugging 2 into that. You realize there's a b part, and the b part would just be put 2 into it. All right?
It's about A4 for that.
I'm sorry, what?
I distributed, it was about the same. Either way.
Okay, all right, yeah, that would have been my guess. It was about 50-50. All right, number 32, I'm looking for something that's different. Number 32 is so much the same that I'm not gonna do that one. What about 34? I see something different about 34. I could either write that down 3 times and multiply it all out and then take the derivative term by term. In section 3.4, I'm going to find a shortcut for this. It's going to be called the composite power rule. But you don't know that right now. So I can't use the composite power rule until I know the composite power rule. So if I want to use the product rule, how does the product rule apply to something that has 3 factors? Well, that's what this actually is, 3 factors. If we call, I'm going to have to use some labeling here. If we call this U for ugly, and we call this B for bugly, and we call this W for wuggly, that's ugly, bugly, wuggly. Then the product rule for 3 factors is going to be the product rule is going to say the first and the second times the derivative of the third plus the second and the third times the derivative of the first plus the only thing we haven't taken the derivative of yet is b, so the first and the third derivative of the second. That's ugly, bugly derivative of wuggly, bugly, wuggly derivative of ugly, and ugly, wuggly derivative of bugly. And now you see why I majored in calculus. That's just fun. Let's do it. Ugly, bugly is, here's ugly, here's bugly. What's the derivative of wuggly? What is it? 2x. I am. I love it. And then here's bugly. Here's wuggly. What's the derivative of ugly? I'm kind of noticing a pattern here. We're going to have that same thing again for ugly, wuggly derivative of ugly. Those are all like terms. All of them have an x, x squared plus 3, x squared plus 3, so I can just combine them, and what would I get? 6x, x squared plus 3 squared. tomorrow, not tomorrow, not even Monday, because we have 3 days to spend on this section. This section has a lot. So Wednesday, we'll get to the composite power rule, and we'll find how we could have gotten from here to here in just one step. But that didn't turn out as bad as I thought it was going to be, since U, V, and W were all the same terms. It ended up not being so bad. I can combine. All right. I think for that reason, I'm not going to do number 38. I want to go on to the quotient rule. Number 38. Okay, remember our goals. There's not going to be any fractions because we don't have any negative exponents. So that took care of our first two goals. Our last goal was factored completely as possible. It is.
Question.
Yes, ma'am.
Since you just took the two terms and made them squared, how did you get from 2x to 6x?
Let me correct something you said. You said I took two terms and made them x squared plus 3 squared. I didn't take two terms. I took two factors and made them this. This is like 2 cows plus 2 cows plus 2 cows. That's 6 cows. 6 cows times 1. This is the like term part is the whole x times x squared plus 3 times x squared plus 3. Just call that cow.
Or imagine that it's just like a constant outside.
Yeah. This is 2 somethings plus 2 same somethings plus 2 same somethings is 6 somethings. Cool. Any other questions about that one? All right. I had number 38 circled, but I don't want to take time doing it. It's going to be a little bit uglier than this one. Yeah, it's ugly again, but it's going to take some more work. And I'm not even sure you have one quite that bad in your homework. You have 37, but it won't be quite as bad as this one, because this one has a trinomial factor, and those are all binomial factors. It's medium ugly, no matter what. All right, let's talk about the quotient rule. Quotient rule. Quotient rule is even more. Hey, y'all stop talking, please. Quotient rule is even more fun to say than the product rule. You could say it this way. You could say the derivative of f over g is g derivative times the derivative of f minus f times the derivative of g divided by g squared. Or you can say these words. You say these words to yourself on about 3 columns, and they're stuck in your head forever. Derivative of the numerator over the denominator is the denominator derivative of the numerator minus the numerator times the derivative of the denominator divided by the denominator squared. Y'all want to prove that using the definition of the derivative, or do you want to trust that? Just trust it. I think the proof is in the book, but I would just trust it if I were you. All right. Make one point here. In the product rule, you said it really didn't matter in which order I did first derivative of second plus second derivative of the first, because that's addition order doesn't matter. What about the quotient rule? Is the same thing true in the numerator of the quotient rule? No, it matters in the quotient rule that you start with the denominator derivative of the numerator. All right. Also, when we used the product rule, we said sometimes you can avoid having to use the product rule by multiplying everything out. That'll turn out to be true with the quotient rule as well, but not on number, this example. Not on this example, because there is a way I could write it as a product. I could write it as t squared plus 2 times 2t minus 7 to the negative 1. That wouldn't end up being any easier. You just need to make friends with the quotient rule, because sometimes that's the easiest way to do the problem. And this one would be easier with the quotient rule than changing that to a product. So help me talk myself through this. I start with what? These words right here. I start with the denominator.
Leave the nuns alone.
Start with the denominator, then what? Derivative of the numerator is 2t. I like it out front because that's where I like my monomials. Denominator, derivative of the numerator. Minus what? Numerator, t squared plus 2, times the denominator, derivative of the denominator, which is just 2, all divided by what? And then you check it real quickly. Denominator, derivative of the numerator, minus numerator, derivative of the denominator over the denominator squared. That's right. I'm going to zoom in so you can see it better. If there was something I could factor out of the numerator, I would. But there's nothing I can factor out of the numerator, so what's my fallback method? Just distribute and combine like terms. Oop, down to typo. But only because I'm checking. What typo?
That's more so.
Yep. And then I don't have much room here. I should have written smaller. That's 2t squared minus 14t minus 4 over 2t minus 7 squared. And I'm so proud of you. If you got that far, I am probably not going to minus 1 you. But what guideline have you not followed completely if you stop right there? You can at least factor out a 2. I don't think there's anything else you can do. I don't think after I factor out a 2, there's not going to be factors of 2 that have a difference of 7. So that's good enough. Or factor it. If I had to find out what made this 0, I can already, or undefined. That's the two things we're usually going to be interested in. What makes the denominator, what makes the derivative 0 or undefined? I can already tell you what makes it undefined. What would make it undefined? 3.5, 3.5, 7 over 2, whichever way you got it. How would I find what makes it 0? What would it take to see what makes that numerator 0? It won't factor. I can factor out a 2, but it wouldn't factor past that. So what would it take? It would take the quadratic formula.
Ew.
It never goes away.
Ew.
All right, but that's not our goal today. All right, number 12. I could write this as t to the negative 3 times cosine t and use the product rule. I don't think that would end up being easier. And I'm not afraid of the quotient rule, so I'm just going to use it. It begins with what? All right, there's the denominator. Times the derivative of the numerator is what? Negative sine t. If you don't use parentheses, that's going to end up looking like t cubed minus sine t. So don't do that. Denominator, derivative of the numerator, and then what? Minus the numerator, then what? 3t. Derivative of the denominator is 3t squared, all over what? T to the 6th. Because t cubed squared is t to the 6th. Then what? Remember the goal, single fraction, we got that. No negative exponents, we got that. Factored completely as possible. I could factor out a t squared. I bet, since both of those terms have negative coefficients, they probably factor out a negative t squared. Not wrong if you don't, but I'm just saying in the back of the book, they probably do factor out a negative t squared. And what would that leave you for the first term? T sin t. And what would that leave you for the second term? Plus 3 cosine t. Double check it. Does that multiply back together to give you what we had on the line before? Yep, it would. I might minus 1 you right here because there's one obvious thing you need to do, and what is that?
T square out of t to the sixth.
Since you factored out the t square, you can cancel it with a t square in the denominator. That's just reducing a fraction. You should always do that. Negative in front of parentheses, t sin t plus 3 cosine t over t to the 4th. My guess is that's how the answer in the back of the book will be written. If you distributed that negative or didn't factor it out to begin with, that's okay. There are times, though, that it is easier to rewrite the function than use the quotient rule. Let me give you a guideline for when it's easier to rewrite than use the quotient rule. You need to remember these two ideas right here. When the denominator is a monomial or the numerator is a constant, those are two times that it's easier to rewrite the function than use the quotient rule. Just be careful not to do anything illegal with fractions. It is true that if you have a plus b over c, you can separate it into these two fractions. It is not true if you have a over b plus c that you can separate it into those two fractions. Because these don't have a common denominator. You couldn't add it back together and get this. All right, so how does that apply to these three problems? First example, the denominator is a constant. How could I rewrite that and not have to use the quotient rule? That's just 3/7 x squared minus 5/7. And how easy is that to take the derivative of? Super easy. What would it be? 6/7 x. Would we get the same thing by the quotient rule?
Probably.
Would it be a lot uglier? Watch out for the denominator's a constant. If it is, you don't have to use the quotient rule. Number 24, how could we write that so that we didn't have to use the quotient rule? 10/3 x to the negative 3. So what's the derivative? Negative 10x to the negative 4, which it's easy to rewrite as negative 10 over x to the 4th. We would get the same thing by the quotient rule. It would just take us a few more lines. And so sometimes in tonight's homework, unfortunately, you may use the quotient rule and not realize until the end, oh man, I didn't have to use that. This would have been a whole lot easier if I had just rewritten it. You're going to learn that from practice. But there's your two guidelines. When the denominator is a monomial or when the numerator is a constant, it's usually easier to rewrite it than to use the quotient rule. So what about this one? I could use the quotient rule, but what would be easier? That's 2x to the what? 1 minus 1/3 is 2/3. And so what's the derivative? 4/3 x to the negative 1/3. This is an example of when they would probably just leave the fractional exponent in the denominator rather than writing it as cube root of x. The original problem didn't use cube root, so the answer probably won't have cube root. But it would be okay if you did put 4/3 cube root of x. All right. Let's do 6 more minutes worth of examples from the book, just so you can feel confident about starting the homework. And then on your notes, let me do this for you. 3.2, oh, that's not it. That's just the paper I'm writing on. My notes, oh, I already did it for you. Tonight will be, really? Stop at 39? Yep, 1 through 39i. That's the homework for tonight. So let's see if we can get a couple more examples of quotient rule, just for practice. Those of you who will be at SMHS in the library tomorrow morning, help each other with that 1 through 39 if you need to. Make sure you get those right. And if you want to do some even problems and check your answers with your buddies, that's okay too. All right, so which one do I want to do? Number 10 looks ugly. Does that meet one of my guidelines for rewriting to avoid the quotient rule? No, I couldn't just split that into 2 fractions because the denominator is a binomial. So don't do anything illegal. You could write that denominator as 2x to the 1/2 plus 1, but then you're pretty much going to need to use the quotient rule. All right, that was just rewriting the function. Here comes the derivative. What does it begin with? Denominator. Then what? Derivative of the numerator. Then what? Minus the numerator. Then what? Derivative of the denominator. What would that be? All right, I'm using just term by term here. 1/2 times 2 is 1. X to the, subtract 1x, 1 from the exponent. Actually, that's all, because the derivative of 1 is 0. So far, so good? Don't forget your denominator. Denominator squared. What do you think we should do next? This looks like another one of those simplifying expressions from calculus. What would you do next? I thought somebody might say factor out an x. You could factor out an x, but this will be easier if you simplify this before you worry about factoring. So add those exponents. 4/2 plus negative 1/2 is 3/2. I can tell you the most illegal thing I see simplifying these rational expressions. Friends don't let friends cancel illegally. That's a t-shirt too.
These are racist.
Yeah. The most illegal thing I see here is illegal canceling. You can't cancel that because it's part of a term. So what do you have to do instead? You could distribute the 2x, but our goal is factor completely as possible. So I don't want to have to distribute and then undistribute. I want to factor out an x. If I have a GCF, I'm going to factor it out. That's the lowest power of my x's, so factor out an x to the first. That leaves me this from the first term. What exponent is left here if I factor out an x from an x to the 3/2? Just say 3/2 minus 2/2 is 1/2. And don't forget your denominator. And then what can you clean up? Well, inside the brackets, you could distribute that 2. And then you have like terms you can combine. That's about it. Other than changing the x to the 1/2 back to square root, which you could because the original problem had a square root in it, but that's all the cleaning up you can do. That meets all of our guidelines, single fractions, no negative exponents, factored as completely as possible. All right, we didn't get to do nearly as many quotient rule examples as I would like to, but maybe that's okay, because there's not going to be anything different. It's just more practice, 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 and maybe you will benefit more from practicing than you would from just watching me do more examples. Yes, sir. Got it? Okay. All right, so the homework is 1 through 39. Bye. See you Monday.
About yesterday's